Hello everyone, my name is Liang Qi, a fresh PhD student in Tsinghua University. It's a great honor for us to attend this competition, and I will represent our team, Barents Sea, to introduce you with our work. Our presentation is structured in the following way. After the background, the part 2 and part 3 are our main work, and then I will conclude our work and with our contributions. Over the last 2 years alone, 90% of the data in the world was generated. However, traditional statistics on the monthly or yearly frequency fails to reflect the rapid change in the economy. In the field of maritime studies, the publications of the statistics regarding port performance not only comes in a relatively low frequency, but also is often delayed and not fully accessible to the public. It brings us to an important and interesting question: how can AIS be used to redefine port performance figures? With these questions, we will use AIS and build a real-time port performance monitoring platform. This platform considers 3 pillars. The first is the port throughput. We propose a high-frequency throughput calculation method. And the second is the port congestion. We propose 2 congestion indicators to show the efficiency of a port. And the second is the port connectivity. We propose a holistic AIS-based port connectivity index system. To realize these objects, we developed an innovative algorithm to identify berth and anchorage areas automatically and precisely. The berth and anchorage area are based on the 2 layers of a DeepScan algorithm, which is a density-based algorithm, a clustering algorithm. So in the first layer DeepScan, we first remove the noise points and identify the unique port visits and clusters of staying area for each port visit. And in the second layer, we propose 2 parameters to reflect the characteristics of a port. And by iterating the DeepScan algorithm until converging to the threshold, we will finally identify the berth and anchorage area precisely. Here we show you an example of Ningbo Zhoushan port. By adjusting the parameters, we can see in the last iteration, that is the iteration 3, the identification of the berth and anchorage areas are more precise and perfectly match to the real map. So our first part is the port throughput. Here we propose a port container throughput estimation map model to capture the high frequency of the port throughput. This model consists of 2 important parts. The first is the ship berthing time estimation, and the second part is the port loading and unloading efficiency estimation. And these 2 parts are based on 2 different methods. Here we use the data in 2017 to test our model and compare the estimation results with the actual throughput data and show the errors in this table. We can see that the estimation error in 2017 are roughly within 5%, which indicates that our model is with high accuracy. And also we test our model with the recent 2020 data, but due to time limits, we only derived around 20% of the total sample, but we can see that the distribution of the ship's length of our sample are quite similar to the distribution of the total sample. So this will make our estimation still reliable. We show you in the right figure, we can see that in the week after the outbreak of the COVID-19, you can see the significant declines of the port throughput for most of the ports. And based on our algorithm, we propose 2 congestion indicators here. The first is the delay ratio, which means the total number of port calls under scenario 1, and that is the no congestion scenario, and divided by the total number of port calls in 1 month. Another indicator is the delay time, which is the average waiting time at anchorage for all port calls. The two figures below shows you these two indicators for Chinese ports in 2017. And the two figures here are using the recent 2020 data, also for Chinese ports. We can see that in general, Chinese ports have a relatively high congestion level, and also the congestion level varies considerably across ports. And the congestion in most Chinese ports is eased since the outbreak of the COVID-19, which is also matched with in line with the fact in China. Here we also show you the port congestion results in other regions like Europe, USA, Japan, and Singapore. And we can see that ports in Europe and America are not as congested as Chinese ports. And also the congestion level of these ports is less affected by the COVID-19. So this comes to our port connectivity part. We propose a holistic port connectivity measure index system based on the AIS data, and this system consists of 6 indicators. First is the vessel visits, and second is the connected countries, and also 3 network centrality indicators. The first is the degree centrality, which represents the frequency of trade exchange for imports and exports, and also closeness centrality to represent the convenience to reach other ports. Also the betweenness centrality to represent the relatively importance to line in any truck line. And the last one is the strategic importance. We use this to reflect the possibility to receive long-distance port calls in the local region. The connectivity measurement system is built following below 4 steps. So after identifying the liner routes and trip lengths using AIS, we can directly calculate this through these 3 indicators. And further, we use the liner routes to build a global liner network. And then we can calculate these 3 network indicators. And the last step, we standardize all the indicators and calculate a total score based on the principal component analysis. Here we show you the monthly connectivity ranking changes post-COVID-19 for 9 Chinese ports. We can see that in February 2020, the port connectivity index of Chinese ports declined significantly and recovered from March. And among them, we can see that Kaohsiung, Tianjin, and Dalian are least affected, and also the reported monthly port calls will validate our findings. In this slide, we select 16 top container ports and also shows you the monthly connectivity ranking changes post-COVID-19. And in general, we will feel like Shanghai is definitely the first place towards connectivity, and actually our results also show this general trend. But we can see that in February 2020, the Singapore replaced Shanghai and ranking the first place. And also another one is we can see that when Chinese ports connectivity declined, the score and ranking of Busan port in South Korea improved. And also in this period, the connectivity of non-Chinese ports is relatively stable. And so as COVID-19 gradually grows into a worldwide pandemic, commercial trade and shipping logistics are sure to be greatly affected. So to evaluate the impact of COVID-19, the natural question we can ask is, does national lockdown have impact on the throughput of a port? To answer this question precisely, we can try to examine whether there is a difference in change of throughput between ports with and without lockdowns, with lockdown as a breaking point. And this will lead to the use of a DID model, which we will explain in a second. Now, if our data tells us national lockdowns do impact throughputs, we would like to take a step further to quantify the impact, and we can do this by finding out how much that difference in change of throughput is. Another interesting question to think about from here is that does that difference change over time? And the answer to this question can actually tell us how fast a port recovers from national lockdown. And here we will need the help of RDD and DID model, a variation of the original DID model which separates the whole time periods into multiple periods instead of just two, and therefore brings more precise and meaningful results. The DID model is a model that effectively identifies the difference in change of the treatment group and the control group in the post period from the time train and the original difference. If the DID estimate the beta 3 is statistically significant, it means the two groups differ a lot after the policy is implemented. We also include CPI as a control variable in our model to depict the economic conditions of a region, as well as weekly and national fixed effects to obtain a more accurate DID estimate. We will mainly consider the two phases of national lockdowns. The first one is China's lockdown announced on January 23rd, with Chinese ports as the treatment group and other as the control group. The second one is the lockdown in Europe and US, announced around March 16th, with the red dotted lines representing the separation and pre-lockdown and post-lockdown. We can tell that throughputs of ports under national lockdown experienced sharper drop in the few weeks after the announcement date, and the DID estimates for both lockdown phases being significantly validates our conclusions. And if we perform DID on weekly port calls, we can draw similar conclusions. To be more precise, we can separate the whole period by week in the RDD-DID model. We will be able to get the change or percentage difference in throughput between treatment group and control group over time, and therefore analysis whether the impact of duration differs between the first lockdown in China and the second lockdown in Europe and US. The recovery of ports in the first and second lockdown doesn't show much difference with respect to weekly throughput, as shown in the line chart on the right. However, if we take a look at the percentage difference in weekly port calls, it is quite obvious from the line chart on the right that China received a strong but short-lived shock from national lockdown, but recovered quickly in the few weeks afterwards, while ports in Europe and US suffer from weaker but continued shock because of national lockdown and recover more slowly. Whether these conclusions are significant needs further validation, as our throughput data was an incomplete sample and may be biased from the general population. And so now let's conclude our work and some contributions. We first propose a fundamental automatic berth and anchorage area identification method, and based on this, we develop a real-time port performance monitoring platform, and also covering port capacity, efficiency, and connectivity. The resulting high-frequency throughput, congestion, and connectivity well explain the impact from COVID-19. We believe it can be applied to real-time event analysis and more applications. Also, our estimated results have been validated with real data and the fact. For most of the ports we examined, the accuracy of port throughput is about 95%. So this shows that our platform is with high accuracy. And thank you so much for your attention. I hope to see you next week.